from section 7.1.3, motional EMF. So in previous videos, we talked about the fact that an electromotive force, which we have defined as var epsilon, is something that moves current, and it's found by integrating some force density over some closed path. Okay. And usually that force was the driving force behind that was some sort of chemical force from the battery inside of the circuit. Okay, but it's also possible to generate an EMF just by moving a loop of wire inside of a magnetic field. Okay, so let's set up this problem. I have a region of space that has a magnetic field. Okay, and that magnetic field is pointed into the page. All right, I have let's do our coordinate system like this, in case that's necessary, x, y, and I have a loop of wire. Let's say it's connected to something that can draw current, and it has a length x here and a height h. Okay, and then we'll say A to B there. Okay, and then I'm going to take this loop and I'm going to pull it with some speed v to the right, which means that every little bit of my wire will move with some speed v to the right. Then I can define a magnetic force that everything is going to feel as the cross of the velocity with the magnetic field. Okay, so I have the magnitudes here of v and b, and the direction is going to be used by the right-hand rule, so v to the right, b in, and that means that is y hat, up. Okay, great. Then I can calculate the EMF by integrating that magnetic force over my whole loop. Okay, I have to do my whole closed path here, but I know that, let's do part of the loop outside of the magnetic field contributes nothing because there's no magnetic field there, so the magnetic force is zero. So I'm left with calculating this over three parts of my loop. Integral of the top plus the integral of the bottom plus the integral of the side, the left side specifically. Okay, so on the top, I know that my path is going to be in the x hat direction. In the bottom, my path is also in the x hat direction, and the side is in the y hat direction. Okay. But my force is in the y hat direction, so all of the integrals where I'm going to be doing a force dotted with a path, when they're perpendicular, those dot products give me nothing. So I can then calculate this over just the side. So that is v b y hat dotted with dy y hat. My path goes from A to B. that dot product gives me 1, and I'm left with V, B, dy from A to B, which is V, B, little b minus A, which is VB times H. That's the EMF. All right, in this case, the force that's being used to move the current is directly coming from the person pulling that loop. So that external work is coming from somebody physically moving the loop itself. Okay. There's another way to calculate this. We can go ahead and calculate the flux through this loop. B dot dA. That flux is, for our square loop, is just B times Hx. And therefore, my EMF is, I guess I haven't defined that yet. Keep going with the flux. We'll take the time derivative of my flux. That is BH dx dt, which is minus BHV. The minus coming from the fact that that a rightwards velocity moves my loop. Let's redraw that really quick. Where this is x. So when the velocity is positive, x gets smaller, so that's what that negative sign is there for. Okay, so this is equal to the derivative of my flux with respect to time. But that is the negative thing that I just had earlier, right? So there is this relationship between a change in flux and the EMF. Where the EMF is a negative time rate change of the flux. Okay. Griffiths calls this the flux rule. And we did this for a nicely shaped object. It doesn't have to be nicely shaped, but it works just fine. Okay, so you can go ahead and mechanically move something, and that movement generates an EMF, which is able to move a current through a circuit.